we all know what quantum devices are, right? Quantum computers and stuff. Or we have a rough idea. We pretend to know. Benchmarking means that you want to check how well it works. So I want to like test it. And we heard talks about this on Monday from Mari, and on Tuesday from also a little bit from Jens. Well, actually, Jens did not mention this, but he also worked on this. The funny thing here is the contextuality. So who of you follows foundations closely enough to know about the tale of the two contextualities? So let me give you a short introduction. And like essentially the first half of my talk will be answering the question from yesterday by Robert Rausendorf about the other contextuality. Because there's the Cohen-Specker contextuality that was formalized almost 60 years ago. And this had some kind of ideas of looking for hidden variable models of a single quantum system. And then in early 21st century, Rob Speckens somehow had a little bit different ideas and formalized something else that he also called contextuality, or at that time generalized contextuality. And since then, like this separated the contextuality people into like two camps that somehow are at odds with each other. So this can be summarized by the following slide, where you can see the Cohen-Specker contextuality enjoyers having like stark problems with the Speckens contextuality. But of course now the Cohen-Specker people are looking at me funnily and saying that, well, this is not the case, we are not afraid of it, it just doesn't make sense. At which point I would say that yes, for you, I have also a second slide, is that people using Cohen-Specker contextuality can complain, the Speckens people can complain that the Cohen-Specker people just think that they're better than the other people. But in all seriousness, I'll try to explain this Speckens contextuality in the first half of the talk in an operational way so that everybody working in quantum information can understand. This is not the way it's written in the original papers by Speckens, or at least I don't really think it's written there, but this is the way I understand it, and all of the math will be the same, and as long as the math is the same, you can provide whatever story you like. So this is my story of how I see it. And it's a rather simple one. You take a set of preparations. So what you take is that you take some kind of laser source, and you have like several buttons that you can press, and this will generate different photons. Or maybe you have some kind of other qubits, solid state, or superconducting, or superconducting, or spins and things like that. But you just have some preparations. And now you also have some measurements effects, because quantum system is completely meaningless if you don't measure it, because otherwise you cannot access the quantum information in it. So we have a set of measurement effects. And now having this, we can make a prepare and measure experiment, which is a rather simple thing. We have a party, Alice, that picks one label I of the preparable states, row I here. She prepares this state. So she just pushes a button on her laser. And Alice sends this state via a perfect quantum channel to Bob. And Bob measures the state and obtains an outcome J. Of course, Bob cannot pick the measurement outcome because that's not how measurements work, but Bob will obtain an outcome. And the result of the experiment is a conditional probability. It's a probability of Bob obtaining outcome J, given that Alice prepared label I, and by Born rule, it's just this number. As you can see, the key thing here is the perfect quantum channel, because a perfect quantum channel is nothing else than an identity map. And as a mathematician, identity map is like one of the most natural maps that you can have in any vector space. It's just like, give back what you have. But experimentally, doing identity is like really hard, because you have to prevent your system from decohering and everything. And essentially, this is the only problem that we have in quantum information and quantum computation, to somehow stop our systems from decohering and decomposing and becoming classical. So this is the hard part. So one can say, okay, if we are doing this experiment and say we would want to separate Alice and Bob by 50, 100, 1,000 kilometers, maybe we can replace the perfect quantum channel by a perfect classical channel. Because doing perfect classical channels is way easier. You can copy classical information many times, which is something you cannot do with quantum information. And then you can have like very simple error correcting codes where you send the same thing 1,000 times. And even if there are errors, you just like vote on the most likely outcome, and somehow the probability of you getting it wrong will decrease. And this is how you can define the Speckens type of contextuality, or prepare and measure contextuality. You can say that these preparations and measurements, and you have to think about both of them at the same time, are Speckens or prepare and measure non-contextual if that perfect quantum channel can be replaced by a classical channel without changing the probabilities. Of course, it's easy to do it if you can change the probabilities, just send something and something will happen, but you want to preserve this thing. And I would say this is a meaningful definition, because it's just asking you whether you can replace a quantum channel by a classical channel, or a quantum system by a classical system, somewhere in the middle of the transition. Okay, so let us now unpack what's written here in the words into math. Because essentially, if you want to prove something, you have to have an exact mathematical definition. Otherwise, you cannot feed this to Lean, or David Gross cannot feed this to Lean. So what we do is that we just take the preparations, we take the measurements, and then we say like, and we say that they are non-contextual, or what we are going to be asking about is, are there operators n lambda and omega lambda such that this inner product, this traces here, can be decomposed into this sum. So what's going on in this sum is that you can imagine this n lambda as a p of em. So these operators, you can think of them as a p of em for like the next 30 seconds, and you can think of these rho omega lambdas as states for the next 30 seconds. And if that would be the case, what you do here is that you just measure some p of em, you obtain a classical number lambda, and you prepare, on the Bob side, you prepare this state, and that's what you give to Bob to measure. But now the question is like, what exactly is n lambda and omega lambda? Because now we can discuss whether we want to do this device dependently or somewhat device independently. Because a natural thing would be to say that we know what these states are, the rho i's, we know what the measurement effects mj's are, we know how they're embedded into quantum theory, at which point we are device dependent, and we should require that these n lambdas and omega lambdas are actually a p of em and quantum states, and then all of these conditions would be satisfied. Oh, and by the way, why do I require these conditions? Because I actually want this trace to be a probability of obtaining classical label lambda, and I want this thing to be, again, a well-defined conditional probability of j given lambda. And this is some kind of normalization condition on the preparable states, and this is the normalization condition of the measurements. You can also do this somewhat device independently, at which point you say that I don't actually know how rho i's are embedded into the quantum system, so I don't really know what these density matrices are. I think I have a guess, but my guess does not have to be correct. Maybe I think these are qubit states, but maybe in fact they're somehow in 100-dimensional Hilbert space, and they only look like qubits to me under a correct angle. At which point you can say that, well, this doesn't have to be a p of em, I just require that these traces are positive, which is strictly weaker condition, because now you're not requiring this to be positive semi-definite for all states, but only for some states. So in principle, this can have some kind of negative eigenvalues if you want to think of this in something like somewhat device-independent way. And the same will happen for these states omega lambda, that they don't have to be states, they can be like pseudo states, so trace one, and just gives you positive probabilities on what you have here. So there's a little bit of leeway, and you always have to specify whether you mean that this is a p of em and these are states, or whether you mean that this can be a pseudo p of em, which means it can have negative eigenvalues as long as this is always positive, and this might be pseudo states, which means they can have negative eigenvalues as long as this is positive. So you have to exactly specify what type of prepare and measure contextuality you mean, and what exact conditions you have. But so far, this should seem as a consistent definition. There's a nice thing about this, that here what we are doing is that if you look at this in a little bit different way, we're somehow decomposing the identity channel into this classical channel in some way, whether we allow p of ems and states, or pseudo p of ems and states, or p of ems and pseudo states, or pseudo on both sides. But in this case, you can actually write this down as this kind of commutative diagram, which is very good, because now the 1.5 category theory enjoyers in the audience can appreciate a commutative diagram. But this is even more interesting, because so what's going on here is that this is the identity channel, and here we are decomposing it into getting a classical label lambda and sending that to Bob, and Bob preparing state before Bob measures it. But actually, you can write down many things in quantum information in this kind of way, and for also joint measurability, simulability, compressibility, you can express them in a way as does there exist a commutative diagram of this form. And if you're interested in that, you should go ask Tim Achenbach, and his whole master thesis was essentially about somehow realizing that these commutative diagrams capture some properties in quantum information. Let's get back to the contextuality, because while this was somewhat probably enlightening, there's more. And I can actually tell you that what this type of operational contextuality, or this prepare and measure contextuality, characterizes, what it means is that something is contextual if it's a proof of no broadcasting. So the spec-ends type of contextuality is essentially what we call no broadcasting. And the fact that you cannot have a universal n lambdas and omega lambdas is a proof of no broadcasting theorem. And I exactly stated it like this because if you Google exactly this formulation, that's a paper that's now published with Pauli and Ropeula and some other, Miriam and some other people from originally from Finland. Here's the main idea how to do that. So for the sake of simplicity, let us assume that the set of effects that we want to consider is all effects, okay? So somehow Bob can perform arbitrary P of M. And then we get that these omega lambdas actually must be positive semi-definite operators or states, because if you have all effects, then this condition just becomes that omega lambda is positive semi-definite operator. Very well, but then we can reshuffle the definition to write it like this. So this is no rocket science. All I did is that I just put one of the traces and the sum inside the other trace. And I get that this is equal to that, and it must hold for all possible effects. But since this holds for all possible effects by something like tomographic duality, or by basically saying that if you have two different quantum states, there must be a measurement that distinguishes them, that means that this state and whatever we have inside of here must be equal to each other as operators or as matrices. So this equality holds. And now we will again use the idea that was already mentioned yesterday by Ruben, because then we can say like, well, if this holds, then I can just put like a tensor power on this omega lambda. And I can define a map phi of rho, which just maps rho to this expression, whatever that is. Now, this expression is going to be a positive semi-definite operator because this number is positive number by our assumptions, and this is a tensor product of a quantum state with itself. And now an interesting thing happens. If you compute the partial trace of whatever you have here, whether over the first system or over the second system, so if you trace out this thing, or if you trace out this thing, you always get the original state by the virtue of this equality. So this phi is nothing else than the broadcasting map for this set of states. And this is the main idea of this paper. We of course go a little bit in depth because now we have to think about what if you don't have all measurements and what about those pseudo cases and so on. But we can have this kind of nice observation that if you have a proof of contextuality in the spec-ends or prepare and measure sense of quantum theory, then this is always equivalent to the proof of no broadcasting. So this is nothing else than just no broadcasting theorem packaged in a very different way. We can also have like two very nice propositions, because now what we can do is that there was a lot of research into broadcasting in quantum theory. If any proof of contextuality is a proof of no broadcasting, we can do it the other way. We can say that if something is non-contextual, then it's broadcastable, and sets of broadcastable states and broadcastable measurements were characterized in quantum theory recently or also in the past. And we can prove these two propositions kind of easily. The first one is that if you assume that Bob can measure arbitrary measurement, then the states and measurements are spec-ends or preparation measurement non-contextual if and only if the states commute. This is saying nothing else that you can perfectly broadcast states if and only if they all commute together, or if and only if they belong to the same context or are in the convex hull of orthogonal pure states and so on. Something similar happens for measurements, although for measurements this is a little bit more involved. And in fact, for some time I attempted to prove that this will also lead to commutativity, but this is going to be strictly weaker than commutativity because there's a trick. If you assume that Alice can prepare arbitrary density matrix and Bob has some kind of set of measurements that he can measure, then they are PMN non-contextual if and only if all of these POVMs that you can have here that Bob can measure are post-processings of a single norm 1 POVM, which basically means that there's a one POVM from which you can post-process everything you have here, which sounds like joint measurability, but the POVM has to be norm 1, which means it's stronger than joint measurability, but weaker than commutativity. So it's somewhere in between. And if you look up the paper and also the non-broadcasting results, then there's exact characterizations what can happen here. And in order for this to be non-trivial and not equal to commutativity, you need to have at least 5-dimensional Hilbert space. So for qubits and qutrits, this will give you commutativity. But in 5-dimensional Hilbert space, you have enough space to do something more interesting. Also, in this case, if we want to see no broadcasting in this way, we should think about that case when we have the pseudo POVMs and pseudo states. And in this case, it's not so easy to discuss because it's not going to be equivalent to exactly broadcasting, but it's going to be equivalent to some kind of pseudo broadcasting because you have pseudo POVMs, pseudo states, so it's going to be pseudo broadcasting, which means you're not going to have you're not going to be broadcasting your states using a channel, but only some map which is positive whenever you need it to be positive. But in this case, it's a bit harder to decide when is something pseudo broadcastable or not, but we can still develop hierarchies of symmetric extensions that can check for this. And we did that. It's also in the mentioned paper. And if you have this hierarchy of symmetric extensions that check for that, you can actually code it on your computer and you can solve it on the computer. So for example, if you take one of the famous scenarios in the spec and compatibility, which is the Mazurek scenario, where you have some states and some measurements, you can then ask for what value of dephasing and depolarizing noise this is contextual or non-contextual. The hierarchy will give you this type of result, that we have some kind of bound given by the non-contextuality inequality, which we know it's necessary and sufficient. Then we have this green region where there is 1 to 3 pseudo broadcasting, so we know it cannot be contextual there. Then we have some region where we have 1 to 2 pseudo broadcasting, but not 1 to 3 pseudo broadcasting. And this 1 to 2 and 1 to 3 means that you give in 1 copy and get out 2 copies, or you give in 1 copy and get out 3 copies. And then you have some region where it's not broadcastable at all, so it's contextual. So somehow, in this sense, you can do numerics for this, and you can actually code them on a computer and run SDPs and get nice results, or these type of results. Another thing that we can do with this contextuality is that we can actually relate it to entanglement. Now, this is going to be a little bit more involved, and this is collaboration with Otfried Kühne, because now it's not going to be exactly one-to-one, but somehow the contextuality is going to act as a precondition for entanglement. So it's going to somehow tell us something about the entanglement, but it's not going to be exactly that. So, but here's the main idea. Whenever you have an entangled state measured by Alice and Bob, like it doesn't really matter when Alice measures and when Bob measures if you assume that the state does not decohere. So you can say that without loss of generality, Bob will measure first. But if Bob measures the state, then somehow Alice will effectively get some kind of effective post-measurement state on her side, which is going to become the sigma. And this we can call remote preparations. So if you have entangled or bipartite state and Bob measures it, you can somehow think of this as preparing a state on the side of Alice. On the math side, this is just reshuffling traces and adding some partial traces. On the operational side, it's just saying that this is now going to become that. And in this way, we can relate entanglement and contextuality as follows. So the main idea is that Alice and Bob now share a bipartite state. Bob measures some POVM and obtains the outcome, and he announces the outcome. So now the state that Alice effectively has in her lab is going to be given by this partial trace, but it's only proportional because you still need to normalize this, divide by the respective probability, because this, strictly speaking, is not trace 1, so it's not a density matrix. And we can now define the set of all remotely preparable states, which means that you fix this state and you assume that Bob can measure whatever, and then you get some kind of set of states on Alice that Bob can in this way prepare for Alice. So we now have set of states on Alice. Alice can perform arbitrary measurement. We can again ask about contextuality of this thing in the prepare and measure scenario in this case. And we get these nice results that the set of these remotely preparable states on Alice is prepare and measure non-contextual, implies that the state is separable. And if the state is separable, that implies that this set is PMN non-contextual. And what's going on here is that we add arbitrary small perturbation to the quantum state. So this perturbation can be arbitrarily small, and this works for almost all states that you can add here, so including separable states. And this is essentially just to fix some kind of, just to satisfy some kind of full rank condition. You know, you add epsilon noise and then your 0 eigenvalues become epsilons and everything will work out just fine. Okay, so in this way we can prove these 3 nice implications, but it's not an equivalence. And in fact, you can also have a counterexample that equivalence is not really here possible because there are cases where you just need to add this to make it work. But now, having this, we can start doing stuff with this. We can start deriving stuff from here. Because now we have related entanglement theory and contextuality theory. So now what we can do is that since we related non-contextuality and separability, and both of these things were kind of heavily developed, we can somehow take results from entanglement theory and push them onto contextuality, but we can also take results from contextuality and push them onto entanglement theory. This is one way easier, the other way harder. Because if you give me a non-contextuality inequality, because of some kind of the structure of this result, I can actually exactly derive entanglement witness, and I'll be sure it will be an entanglement witness. If you give me an entanglement witness, I can design a non-contextuality inequality, but then I actually have to go to the framework of non-contextuality and prove that it's a valid non-contextuality inequality. So one way it's easier, the other way is harder. Let us start with the easy way. And here what we do is that we take the non-contextuality inequality derived by Mazurek for this Mazurek scenario that I briefly mentioned before. And we can prove the following proposition, but now I just want you to look at two parts. Let rho AB be separable quantum state, forget the rest, and then we get some kind of inequality that holds for separable states. And this is an entanglement witness, because this is some kind of linear inequality in rho AB that's satisfied for separable states. Of course, one can now ask, like, is this a trivial or non-trivial entanglement witness? You know, because trace with identity is always positive no matter what state you have, so you can say it's an entanglement witness because it's positive for all separable states, but then people would say this is a trivial entanglement witness because it doesn't detect anything. And one can now ask, does this detect something? So what you then can do is that you can go back to the contextuality scenario and look for the canonical or the standard way the contextuality inequality we use to derive all of this is violated. And once you plug all of the numbers in, you get the following entanglement witness. So this is something like trace with sigma x, because this is on qubits, and sigma z less than 4/3, 4/3. Now this is nothing else than a weaker version of the standard entanglement witness that xx plus zz is less than 1. But I mean, this is still an entanglement witness that you can violate, it's just not the optimal one. But anyways, you can derive it in this kind of very strange and obscure way. But take this as a proof of concept. It just works. It's also not going to probably revolutionize the field of entanglement detection because we have way more entanglement criteria than non-contextuality inequalities. But that just means that we have to go the other way. So can somebody give me like a very simple entanglement witness? Yes, exactly. CHSH is an entanglement witness, right? That's exactly what we can do here. So we can take a CHSH inequality and we can hit it with a hammer several times, and it will become some kind of inequality that involves preparations and observables. But then we don't know whether this is a contextuality inequality, but we have to actually go and now check for all possible sets of states and sets of measurements that this still works because of the structure of those two implications. But in this case, we can actually do that, and we can actually derive a non-contextuality inequality from CHSH. And it just tells you that you need to have two pairs of states such that they always add up to something. There can be also some kind of offset between them. And you need to have operators bounded from -1 to 1. So these are the observables you would have in CHSH scenario. And then something is less than 2. So you can clearly see how this was stolen from CHSH inequality and then beaten into contextuality inequality. Very well, so we can also go the other way. And that's nice because there's way more entanglement witnesses than contextuality inequalities. But now, here's the important question. What is this good for? I mean, of course, these are now nice foundational results, but what can we use them for? You know, like, what is this good for? Even more importantly is the question of how is this going to help Sunny and her friends save magic in Equestria? Well, obviously, they can build a quantum computer, and contextuality will provide the magic. But in all seriousness, we can now go a little bit further with this thing. We can take more Bell inequalities and put them into the form of contextuality inequalities and do stuff with that. Because, you know, we can actually go beyond what I showed you for CHSH and prove a more general theorem as follows. Consider a d-dimensional Hilbert space and have some kind of subnormalized preparation sigma ax that add up always to the same thing for all x. So the steering people would call this the steering assemblage, and have a set of P of EMs. So here B labels the outcome and Y labels the P of EM. Then I can construct this probability PAB given XY by tracing the assemblage against the P of EM. But now this assemblage is not a steering assemblage, it's something, it states I can prepare obeying this linear constraint, and these are P of EMs. And the first thing I can prove is that this conditional probability is Bell local, or has a Bell local model, if and only if the preparations and measurements are prepare and measure non-contextual. So here I'm going a little bit beyond the entanglement theory, and I'm just straight going for Bell inequalities and relating Bell locality with contextuality. Even nicer thing is that I can say that, well, if you now have a Bell inequality, of course, if this is non-contextual, then it's not going to be violated on this thing. But if you have a Bell inequality, which has a dimension-dependent bound, which means you can bound the violation of the Bell inequality depending on the dimension, then the bound will transport as well. And this is again no hard calculations, because all you have to do is that you have to realize that the sigma A given x, this is something like the bipartite state share between Alice and Bob measured by Alice. And these are the measurements of Bob. So these relations, they're not very hard to prove, and probably you can do it within the coffee break. But the nice thing is that now what we can do is that we can go to the Bell inequality people and we can ask them, hey, do you have some Bell inequalities with like dimension-dependent bounds that we can use to construct contextuality inequalities with dimension-dependent bounds? Because this would be actually cool. We can do two things with that. We can take a quantum computer and have it violate contextuality inequality, proving that it's not classical, as long as the standard loopholes and assumptions are satisfied. But we can also prove how many qubits or what's the dimension within the quantum device that you have. Now, I find this interesting because there were methods previously developed to somehow prove how many qubits you have in your quantum computer or what's the dimension of this quantum system. But they always suffer from a problem that you can either certify that the quantum dimension is 5 or the classical 5 or higher, and the classical dimension is, say, 15 or higher. So it somehow does not rule out big enough classical systems. And this is a problem because this is a huge classical system that I have in my pocket. This is have like, 1 gigabits of RAM? But if we do it with contextuality inequalities, give or take some loopholes and assumptions, we can actually rule out that what you're using is a classical phone, but you can also prove how many qubits there are. So we just now need a good Bell inequality. And a good one is the CGLMP4. So here A and B ran from 0 to 3, X and Y ran from 0 to 1, and this is the inequality. And please don't even read it, it's just some mumbo jumbo of characters. This P, A less than B, this is actually sum over all values of A and B where the constraint is satisfied and so on. The nice thing is that the X2, so the dimension-dependent bound for qubits is 0.2, and the dimension-dependent bound for qutrits is 0.315. And the maximal violation happens if Alice and Bob both have a 4-dimensional system, so 2 qubits, at which point it's analytically known that you can reach violation of 0.36. Okay, so what do we have now? We have Bell inequality with dimension-dependent bounds and a known violation how to reach that. We have a method to transform Bell inequalities with dimension-dependent bounds into contextuality inequalities with dimension-dependent bounds. So we just plug the first one into the second one, and we get CGLMP4 contextuality inequality with dimension-dependent bounds. And this is nice, because now if a quantum computer violates this, you can not only prove that it's not classical, you can also prove that it has at least 2 qubits. And moreover, once you compute everything, you can see that the maximal violation is given by these preparations and these measurements, which is kind of nice because these are projective measurements and these are proportional to projections. And there's like a whole bunch of, coefficients in here that are not really that important. So now what you can do, or now what we did, is that you can send an email to the people in Stockholm, to Mohamed Buran and his group, and you can tell them like, hey, would you mind measuring this? What they did is that they took their Sagnac interferometer and they actually measured this. So Now this is somehow the schematics of the setup they had, and you can see that there's like a preparation part, and then this A branch, here they measured the CHSH contextuality inequality that they showed several slides earlier, and this was just something like a proof of concept that they can do it. And that took them maybe one afternoon. And here they actually measured the CGLMP4 contextuality inequality, and that took them over a year, I think. Also, you see that this is the standard SANAC setup with like hockey pucks and blue boxes and these lampshades and stuff like that. I have completely no idea how this works. I understand only the theory. But it's kind of cool that somebody else does. I also really like how this box is labeled BS. It's a beam splitter. Okay, and they actually get that, they get experimental violation of 0.3631 plus minus 0.01. And this is how we can know that they actually measured it, because there's like an error bar. And this is compared with the theoretical value, and it's within the bounds. And also this is strictly higher than the qutrit bound. So they must have used at least 2 qubits to measure this. And the 2 qubits were like which path and polarization of the photon. So now I know that their SANAC interferometer actually does have 2 qubits, and it's not a classical system, which probably could have been done in an easier way, but I find this one more interesting. And these are the results of how to benchmark quantum devices, because in principle, the SANAC interferometer is a quantum device, and you can do the same things on a 2-qubit quantum computer, say with trapped ions, and you can still violate this inequality and get some numbers like this and say that, okay, you have 2 working qubits that can do this. And that leads me to the take-home messages. That's the 3 of them that I would like you to remember. The first one is that contextuality, in fact, can be used to benchmark quantum devices, and it somehow makes sense, and we can use this within the bounds of the loopholes that are embedded in the contextuality setup. Moreover, the theory is far from settled, and we don't know how to exactly do it in general. So everything I showed you is somehow very specific examples where we derive this, but there is no overlapping huge theory package of how to do this for arbitrary dimensions and so on. So there's a lot of theory work to do in that direction. But also, the resulting protocols are experimentally feasible. If you go to people building quantum computers, you can give them this stuff and they can actually do it, and it works. You know, it's reasonably, you have like reasonable robustness built into the inequalities that you can allow for experimental errors and so on. And with that, I'd like to thank you for your attention.